So our next speaker going to be Mohamed. Salman, he couldn't make it. Because but he knew that was going to invite Mohamed to start a presentation. All candidates.
Yeah, I can hear you.
Okay. So let me. Can you share us slides on the screen?
Yeah, I can share the screen. Yeah. Okay. Good afternoon, everyone. My name is Mohamed Salman, and I'm excited to present my research work titled On the Robustness of Malware Detectors to Adversarial Samples. This research is conducted at Macquarie University Cybersecurity Hub along a team of talented researchers. I would like to acknowledge the Australian Government, Department of Defence Science and Technology, whose partial funding made this research possible. As the threat of adversarial attacks becomes increasingly more, the robustness of malware detectors has become critical. Adversarial samples, which are slight modification to the binaries, are designed to fool different malware detectors. So in this research, we conducted extensive experiments to see the transferability of malwares and to answer whether we can stop or mitigate the effectiveness of the adversarial attacks. So let's first begin with a simple definition and background of adversarial examples. Adversarial examples are imperceptible slight modification to input data with the goal of deceiving a target model. So here we can see that, let me add a point here. The traditional machine learning, in the traditional machine learning, a model is trained on a clean and unmodified training data. A predictive model is developed and the input data, the original input data is correctly labeled. In adversarial attacks, the attackers add imperceptible noise to generate perturbed data, which is then passed to the predictive model, and a falsified label is generated. In the domain of the image, the adversarial examples are easy to generate since we can arbitrarily make changes to the input file. However, in the domain of malware detections, one of the challenges is that an attacker cannot arbitrarily change the input data without breaking the functionality of the binary. So this is a challenge in the adversarial example generation of malwares. One of the constraints in the generation of adversarial example is that the perturbation must be minimal so that the modified binary or the modified adversarial examples remain similar to the original binary. The second most important constraint in the binary or the malware adversarial example generation is that while the target generated transform binary, it should be similar to the original binary in functionality. As we are familiar, that an attacker can lodge a white box attack or a black box attack. In white box attack, the attacker has full knowledge of the target machine learning model, while in the black box attack, the attacker has limited access to the model and they can only query the model by providing an input to the model and observe or monitor the classification outcome of that model. So the transferability refers to the ability of the adversarial examples generated by an adversarial attacker which are designed to evade a target model to also evade other non-target models. Again, in the domain of image detection, the generation and the transferability of adversarial attacks are well studied, and it's a well established fact that in the domain of image, the transferability can occur. However, in the domain of malwares, the transferability is less explored, and there is a lack of consensus on the transferability of adversarial examples. So the main issue is that to investigate the transferability of adversarial example in malware detection, which we assume that may be limited due to different factors, which I will discuss in the upcoming slides. And the second most important aspect is whether we can effectively mitigate the impact of the adversarially transformed binaries with the help of ensemble of detectors. So we made three critical contribution in this study. First of all, we conducted a comprehensive transferability analysis of adversarial malware attacks across different detectors. We demonstrated that a malware which is targeted to fool one model cannot effectively fool other models. Next, we showed that the ensemble detectors are effective in countering the success rate of the adversarial attacks. Last but not least, and which is another important aspect of this study, is that we demonstrated that an adversarial binary which is significantly transformed can be easily generated with the help of the new signature. So first, let's see how the malware detection works in real world. In real world systems such as VirusTotal, it rarely relies on a single detector. Like if we, for instance, take the example of VirusTotal, it relies on multiple detection techniques. So in VirusTotal, if we provide an input file or a cryptographic hash like MD5 SSH, it provides a comprehensive report that includes its cryptographic hashes. The report also includes the outcome from a list of scanners that are provided by different security vendors, and most of these scanners are machine learning based models. Additionally, SSD VirusTotal include the SSD technique, which unlike different cryptographic hashes like SHA-256 is an MD5, rather than generating a fixed hash over the file, SSD works differently. It breaks the input binary into different small blocks, and then it computes hashes for each of the blocks. Finally, the SSD concatenates the results from each block into a final digest. The outcome sample is in the form of this SSD hash, which we can see. So why we hypothesize that the transferability may be an issue or may be limited in adversarial attacks. We think that an adversarially modified malware binary that particularly evade one machine learning based model may still be caught by other models. So, following are some of the reasons. First, as we discussed, that there are functional constraints in binaries. We cannot arbitrarily change a binary. Secondly, there are limitations in changing the different functions in binaries. You cannot change every functions in a binary. Secondly, different machine learning models are trained with different features. So let's if a adversary successfully evade one model, that generated adversarial binary might not be able to bypass the other models due to the different feature space or the architecture. Third, there is a diversity of detection models in real world, as we show in the virus total example. There are different machine learning based techniques. There are cryptographic hashes. There are locality sensitive hashing technique like SSD. Fourth, there is a trade-off between minimal versus too many changes. So what does this mean? In the constraint, we discussed that the adversary would like to make some minimal changes to the binary to evade detection. But if the adversary made minimal detection to a binary to evade a machine learning detection, and it will also, like, minimal changes can evade the cryptographic hashes. However, due to the structured similarity measures of SSD, it divided a binary into different blocks and compute the hashes of each block. The minimal changes will not be effective to evade SSD. On the other side, if the adversary also try to evade SSD in the ensemble for maybe transferability, if the adversary try to make too many changes, so it can result in making another signature which can be detected by other models. In order to counter these limitations, an adversary may possibly try to obfuscate the binary, which can itself potentially trigger malware detections. So these are the factors that we think can hinder the transferability of adversarial malwares in malware detection. Our sample data test set is taken from the Sorel 20 million data sets, which is a data set of portable Windows portable executable files. The Sorel data set contains hashes, binary files, and Ember features of both the malware and binary files. While the binary files for malwares are provided by Sorel, due to the copyright reasons, the Sorel doesn't publicly make available the benign files. So in order to get the benign files, we take hashes from the Sorel, and if the hash, a corresponding file against the hash is found on virus total, we downloaded it. So in this way, we have a test set of 3,362 malwares and 1,564 benign files. We evaluated three different detectors in our study. All of the three detectors were evaluated individually and as part of different ensembles. The first one is a Markov, which is a state-of-the-art deep learning model, neural network model for malware detection. Next, we evaluated Ember RF, which is a random forest-based model developed on Ember features. The Ember features are a comprehensive list of features which are extracted from binary files, including features from its metadata, byte patterns, entropy, strings, and imported functions. Importantly, we include locality sensitive hashing such as SSD based signature detections in our evaluation. So now let's see how we created transform binaries, or how we generated adversarial binary. So we use a recent tool, the Malware Maker framework, to generate adversarial binaries. We received the private version of Malware Maker framework with the direct correspondence with the author. The private version of Malware Maker is quite effective in generating adversarial binaries against a target model. We launch white box attacks with the help of the Malware Maker against Markov model using its gradient information. For non-gradient detectors like Ember RF and SSD, we use black box attacks to generate adversarial binaries. We use two malware transformations during the white box and black box attacks. One is the displacement. The displacement basically relocates code segments within a binaries, and filling the spaces with the jump instructions and semantic snobs to modify the binary and maintain the same functionality of the binaries. Secondly, we use in place randomization technique, which basically replace original instruction with their equivalent ones to modify the adversarial binary while again maintaining its core functionality. The original malware macro framework had the support to target Markov. However, in order to target Amber RF and SSD, we extended the original malware framework in order to generate adversarial binaries for Amber RF and SSD. So we generated the adversarial binaries for all these model. If we look at this graph, we first generated adversarial binaries against keeping the Markov as target model. So with the binaries generated by keeping Markov model as a target, it significantly the modified binaries significantly drop the accuracy of Markov. However, it has the Markov targeted transform binaries has very little impact on Ember RF and SSD. So this shows that the transferability lack of adversarially transform binaries when Markov as a target. We repeated this procedure for the other two detectors as well. So if we see when the Ember RF was kept as a target model to generate adversarial binaries, it significantly dropped the accuracies for Ember RF. However, it has the transform binaries has no impact on Markov, while it has a very little impact on SSD. Lastly, we repeat the same procedure for generating adversarial binary while keeping SSD as a target. So we can see from the graph that it significantly dropped the accuracy for SSD. However, it has little impact on Amber RF, while again no impact on the Markov model. So this shows that the adversarial examples crafted to bypass one detector were not highly transferable to other detectors. The second issue of this research was to assess the effectiveness of the ensemble detector. So this graph shows the ensemble's performance in terms of the true positive rate and false positive rate. The ensemble of the Markov, Ember RF, and SSD was used first on the original data. Let's discuss the different decision rules and the ensemble. When we kept the minority rules, we can see that it has a very good TPR performance on the original binaries. However, it has a higher false positive rate of 39%. Similarly, while the minority rules perform well on the Markov targeted transform binary, the Ember targeted transform binary with an accuracy of over 99%. However, this has resulted in a higher, very higher false positive rate of over 95%, which shows that the minority rule ensemble is not feasible in detecting the adversarially transformed binaries. Secondly, we use the majority rule voting. When the majority rule voting was applied to the original data set, it gives an accuracy of 97% with a nearly perfect FPR of 1%. So this shows that the majority rule is quite effective in detecting the original malwares. However, on the transform binaries, the effectiveness of the majority ensemble dropped to 76%. all with an increase with the FPR as well. We analyzed this issue, and we found that the increase in the FPR and decrease in the TPR was due to the poor performance of Ember and the ensemble. The Markov and SSD shows a good detection rate in the ensemble, which can be seen that when the Ember RF was the target. Now, since the majority now include the SSD and Markov, we can see that the majority rule in this case have very good TPR as well as a very comparatively low near 20% FPR. On the other hand, if we see the consensus rule voting, the performance of the consensus rule on the original binaries is quite poor. Same is the case with the other targeted transform binaries. So we concluded that the majority rule ensemble provides reasonable trade-off between detection performance and false positives. Now to further solidify our claims of the ensemble effectiveness, we uploaded all the original binaries and the transform binaries to VirusTotal. On the Markov targeted transform binaries, the malware before transformation, which can be seen in the blue lines, was reduced to the line which is shown in the yellow dotted lines. Similarly, for the Ember RF, we can see that the original detection rate in the blue line was reduced to the yellow line from 0.6 to 0.4. Similar cases with the SSD transformation. So all these results shows that while the transform binaries reduce the detection rate from its original, however, none of them were able to fully evade the ensemble. This shows that the ensemble are effective in mitigating the adversarial attacks.
More. You
Sorry?
have 5 minutes more.
5 minutes more. Okay. Yeah. So we see that ensemble of detectors like VirusTotal helps mitigate the impact of adversarial transformations. Our third important contribution was that the highly transformed binaries can be detected. From this graph, we measure the changes in the binaries in terms of Levenstein distance. So this graph shows that in order to evade SSD, the malware Macor framework has to make significant changes. In most cases, the changes were greater than 70% file. On the other hand, for Markov and Ember RF, the changes were less than 10%. So if the adversary make more changes to evade the ensemble or SSD, we trained a random forest and light GBM model to see whether we can detect the highly transformed binaries. So we selected top 20 modified binaries and least 20 modified binaries. On the top 20 modified binaries, we can see that LGM had near perfect detection rate of 97.5%, while on the least modified binaries, the detection rate dropped significantly to 52%. So this verify our claim that the detection that highly transformed binaries generate a new signature which can be easily detected by a highly trained model, machine learning model. So to conclude, we make that adversarial malware does not transfer across different detectors when the feature space is different. Secondly, the ensemble detectors significantly reduce the success of adversarial attacks, as we showed with our ensemble and the VirusTotal. Thirdly, we concluded that the highly transformed binaries are easier to detect. Our future work include, as this research is still in progress, we aim to propose an adversarial technique that can evade multiple detectors while keeping the changes and the binary to minimal. Now, if you have any question, I'm happy to respond.
It can be acceptable amount of feeling for 95% true positive for
Now, can you hear the question?
Sorry, there is so much distortion.
Okay, so the question was, is it acceptable to have a malware detector with 95% true positive?
True positive or false positive?
True positive, no? You said, yeah, true positive. So the malware is detected as malware.
Yes, so if we are talking about the true positive, it is acceptable 95% true positive, but a false positive of 95% is not acceptable.
Yeah, that's too high.
No, yeah, false positive is too high. So if I get back to the ensemble, we are suggesting the majority rule. So with the majority rule ensemble on the Ember RF, the accuracy was around 96%, while the FPR was around 20%.
Yeah. So yeah, next time was no positive, no? Malware malware 95%. The false positive is around 12%. Can you go back to your graph?
Yeah, yeah. Yeah, here.
Yeah. So the false positive rate is around 20%.
Uh, so, uh, so as discussed that in the Ember RF, where the Markov and SSD were the majority, we see that the TPR was true positive rate was around 96%, while their corresponding false positive was around 20%, actually 21%.
The question was whether 95% true positive rate is acceptable for a
Yeah,
malware detector.
yeah, it's
Yes or no answer?
acceptable. Yes, yes.
Okay.
Yeah.
Okay. Any other questions?
Normal video presentation, but I have some observations. The first observation is that you were talking, your complete presentation was on adversarial transferability by taking some malware detectors, and as far as my knowledge is that all three detectors that you managed to attack were actually working on different features. For example, Malware is working on bytegrams, and Amber works on the header fetches. So basically, reference number 4 from Lunga's video that the the used to create the malware is basically like it uses 4 keys. So according to me, like if you create a binary file and try to make some changes in the body of the file and you compare it with a computer which is primarily looking at the address thing. And the converse is also true. Like if you take a detector and sorry, sample and try to modify things, then you need to malware detector like Malcolm where it is only focusing on bytes. It will not understand this thing. So the conclusion, I'm not very sure. Like it should not be transferred to speeches.
It is a kind of a comment rather than a question. Hope you
Maybe you have to repeat the question.
Yeah. Mohamed,
Yeah,
can you hear
yeah,
us?
cool. Yeah, I can hear you. Could you please just repeat the question for me?
Yeah, because it's a comment rather than a question. So the idea was, so the three detector you discuss use different feature spaces in terms of detection. So because of that, modifying the content, for example, when the detector use header information, doesn't much affected the detection. So that was a comment rather than a question. So if you have any thoughts, or if you consider those feedback to improve the work, perhaps that would be useful.
Yeah, okay. Thank you. So the issue was as I discussed it in the malware domain, the transferability is less explored. Like some authors has proposed that transferability exists in malware, but in their studies, the feature space was same. Like same machine learning and deep learning models were used to assess the transferability. However, there was a gap. Like none of the author evaluated the different models with different techniques. So this was the first work to assess the transferability in malware when the feature space is significantly different.
Perhaps you can discuss offline if you want to continue the discussion because of the time interest. Let's thanks the speaker once again.
Yeah, thank you.